Which LLM model sizes can you run on your PC, laptop or tablet, and is there a way to estimate the expected performance? After my last video on small language models, quite a few asked exactly that. How do I know which models actually fit into my machine? CPU, GPU, RAM, VRAM, we'll sort this out today once and for all. I'll be using Qwen 3.5 as the demo model throughout this video, as promised in the comments. What you see here is LM Studio on the left and the Windows Task Manager on the right. That combination is what we'll be working with throughout this video, so you can see exactly what each model does to memory in real time. My CPU is already under some load. That's because I'm running OBS for screen capture in software encoding mode, which runs entirely on the CPU. Keep that in mind, it's using a noticeable share of my 8-core processor. System RAM 32 GB. What you see consumed here is the baseline. Windows 11, LM Studio, Task Manager and OBS running in the background. My CPU has no integrated graphics, but as you can see I have two dedicated GPUs. For today's video I'll be working primarily with the AMD RX 6800. In my next video I'll show how both cards, so including the Intel Arc A770, can work together to run significantly larger models. If that's something you want to see, subscribe and hit the bell. The RX 6800 already has a small baseline load that won't affect inference in any meaningful way. The value we care most about is this one: dedicated GPU memory. That's our VRAM. Note that what's labeled GPU memory here is actually the sum of dedicated GPU memory and shared memory. That shared memory portion is just regular system RAM, in my case DDR4, that Windows uses as an overflow when dedicated VRAM runs out. We'll see later exactly what that does to performance. Spoiler, it's not good. Our starting point, roughly 1.6 GB of VRAM, already consumed at baseline. If you want clean numbers, close your browser, it tends to consume a surprising amount of VRAM. A few LM Studio settings worth checking. In the hardware section, make sure your primary GPU is enabled. In my case, that's the RX 6800. The offload KV cache to GPU memory switch is a double-edged sword. You can turn it off to save VRAM, and as we'll see, the KV cache does consume a significant amount. The KV cache is essentially the chat history, stored as key value pairs for faster processing. If you offload it into system RAM instead, that data has to travel over the PCIe bus, which is slow. Use this only if you absolutely need to run a model that's slightly too large for your VRAM and you're willing to accept the performance hit. It should never be your default. In the runtime settings you can choose the engine that processes the model. Vulkan is generally a safe choice and works across hardware. You can also run models purely on the CPU, we'll come back to that. If you have an NVIDIA GPU, the CUDA variant is likely your best option and may outperform Vulkan. Let's load our first model. I'm starting with Qwen 3.5 08B, deliberately small, and I'll explain why in a moment. For quantization, Q4KM is usually a solid default. I'm intentionally choosing Q80 here because it gives us a file size of almost exactly 1 GB, which makes the memory math easy to follow. Before loading, there's a useful experimental feature in LM Studio. Hold the Alt key and you'll see an arrow appear. Click it for more detail and more control. You can see the estimated memory usage, roughly 1.1 GB from our VRAM. GPU offload is the slider you want at maximum in almost every case. If the model isn't fully in VRAM, performance drops, often dramatically. The context length controls how much conversation history the model keeps in memory at once. This directly affects the KV cache we mentioned earlier. For most everyday tasks, 4K tokens is plenty. 8K covers longer documents and extended conversations. But what if you set context to maximum? Qwen 3.5 supports up to 262K tokens. Let's load it that way and watch what happens in Task Manager. From our 1.6 GB baseline up to 6.5 GB, almost 5 GB consumed by the KV cache alone before a single word has been generated. And this is a 1 GB model. And notice, the jump happens immediately on reload. LM Studio pre-allocates the entire KV cache at load time, not gradually as you chat. Change the context settings, reload, and you see it instantly in Task Manager. The context slider is not just a chat feature, it's a VRAM setting. Now the other direction, I'll reload with context set to the absolute minimum. Around 100 tokens, 0 doesn't work. At minimum context, roughly 1.2 GB additional VRAM. Back to 4K context. At 4K, 1.7 GB. I'll be running all further tests at 4K context. That's enough for the demo prompts and it keeps the numbers comparable. I promised we'd also estimate performance. Here's how. If you know your GPU's memory bandwidth, you can calculate a theoretical maximum in tokens per second. You can find this on Tech Power Up, search your GPU name plus specs. The RX 6800 comes in at roughly 512 GB per second. During inference, the GPU has to move the entire model, weights plus context, through memory for every token generated. At 4K context, our 0.8b model occupies about 1.7 GB. 512 divided by 1.7 gives us roughly 300 tokens per second as a theoretical ceiling. This is a rough upper bound, not a precise prediction. There are factors that can push performance higher, like infinity cache, mixture of experts architectures or speculative decoding. And there's one factor that will always push performance lower over the course of a conversation. As your chat history grows, the KV cache grows with it. More data to move per token means your tokens per second will naturally decrease the longer the conversation runs. For a quick rule of thumb, this is more detail than we need. Just keep in mind the formula gives you the ceiling at the start of a fresh chat. Let's check the actual speed. I'm using a technical diagnosis prompt I've used in previous videos. Around 130 tokens per second, well below our theoretical 300. At this model size and these speeds, even screen scrolling during capture adds measurable noise. The formula becomes more accurate as model size increases. Still, keep that number in mind because it helps us estimate what larger models will do. One more reason to start with a model this small, it's a smoke test. If you have 4 or 6 GB of VRAM and you're not sure your setup is working correctly, load something this small first. If the GPU isn't being used at all, you'll see it immediately. And we can use the speed to extrapolate what larger models will look like. Let's scale up. Qwen 3.5 4B Q4KM quantization. File size is roughly 3 times the 08B model. Let's see what that means for VRAM. Around 4 GB total including a 4K context window. GPU offload on maximum. Worth noting, with a clean baseline, this model fits into a 6 GB GPU at 4K context. New empty chat, I want to start with a clean context window. You saw 130 tokens per second with the small model. What do you expect for something 3 times the size? 70 tokens per second, that's genuinely fast for a model of this size. Our formula at 4 GB gives a ceiling of 128. We are hitting about 55% of that. The formula gets more useful as models get larger. The scaling rule holds directionally. More model size, less speed, proportionally. And the output quality at this size is solid. In my benchmark from the last SLMs video, this model scores full marks on this prompt. Before we push to the limits of this GPU, a quick note on Qwen's 3.5's architecture because it matters for what comes next. The small variants 0.8b, 2b, 4b and 9b are standard dense models. Every token runs through every layer every time. The larger variants 27b and 35b use a mixture of experts architecture. In a dense model, all parameters are always active. In a MOE model, only a subset of specialized subnetworks, the experts, are activated per token, specifically those best suited to the current input. This has a direct effect on our bandwidth formula. If only a fraction of the model's layers are traversed per token, the effective memory movement per token is lower, which means higher speeds than the raw model size would suggest. One important catch: MOE models still need all their experts loaded into VRAM or RAM, even the inactive ones. So they are actually more memory hungry than a comparable dense model, but faster once they fit. For everything we've tested so far, dense architecture, our formula applies as is. Let's find the practical limits of the RX 6800. I'm loading a 27B variant. This is one of the MOE models. With available quantizations, we can get close to the edge or just over it. Watch the dedicated GPU memory and the shared memory. You can see shared memory has grown. Not everything fits in VRAM anymore. Some data has spilled into system RAM. If you're running a monitor through your integrated GPU rather than your dedicated card, you can recover some of that baseline VRAM, potentially enough to fit slightly larger models. Still around 20 tokens per second. That's surprisingly good for a model of this size with confirmed spillover. The MOE architecture likely explains this. The layers that spilled into shared memory are probably inactive experts, layers that simply aren't called for this particular prompt. So the PCIe penalty is smaller than it would be for a dense model where every layer matters every time. Now the same test with a dense model. Qwen 3, 32B, no MOE. At 17 GB, it can't fit in the RX 6800. Shared memory usage spikes significantly. 3.3 tokens per second. That's the real spillover penalty for a dense model. Every token requires every layer, nothing is optional, nothing can be quietly left in slow memory without consequence. This is the number to remember. Crossing the VRAM limit on a dense model doesn't degrade performance gradually, it collapses it. And this is precisely where a dual GPU setup becomes interesting. But that's the next video. Let's wrap up with what we've learned. Start with a small model. Even a 1 GB model tells you whether your GPU is actually being used and gives you a baseline speed you can extrapolate from. The bandwidth formula, GPU memory bandwidth divided by model size in VRAM, gives you a theoretical ceiling for tokens per second. It's a rough upper bound, not a precise prediction. It gets more accurate as model size increases and it assumes a fresh empty chat. As your conversation grows, so does the KV cache and your speed will drop accordingly. The context slider directly affects VRAM consumption at load time, not gradually during the chat. 4K to 8K covers the vast majority of everyday use cases. Maximum context is almost never worth the VRAM cost. Spillover into shared memory, your system RAM, is not a crash, but for dense models, it's a severe performance penalty. For MOE models, the impact is smaller because inactive experts can sit in slow memory without being called. One thing I wanted to show in this video but couldn't do cleanly is CPU inference. OBS was running on my CPU during recording, which compromised the numbers. Here's what the math says instead. DDR4 3200 gives roughly 51 GB per second of memory bandwidth about 1/10 of the RX 6800. At 4 GB model size, that's a theoretical ceiling of around 12 tokens per second, and a real-world CPU performance lands below even that because CPUs lack the parallel compute architecture of GPUs. The CPU is your fallback, it's not your plan. Next up, the dual GPU setup. The Intel Arc 770 adds another 16 GB of VRAM to my machine, and combining both cards for LLM inference is less straightforward than it sounds. If you want to see whether it actually helps and by how much, subscribe, leave a comment, and I'll see you there.